Hey everyone, welcome to the channel. My name is Jagat, or Jugs for short. I haven't been building stuff for long, but I've found that it's something that I love doing, so I decided to make a YouTube channel. Right now, computational physics and mechatronics are two fields which really interest me, so stay on the lookout for videos where I'm building stuff in these realms and telling you guys about my experience and honestly probably asking for help with some of my projects. But without further ado, I made this fun visualization of gravitational quantities that I wanted to share with you guys through a couple videos. So this first one, I'll explain the physics and do a couple derivations behind the simulation. And the next, I'll detail how I went about the actual coding side of things. And shout out Mr. Onur gundogdu, who I made this simulation in consultation with. Okay, so the first question that we need to answer, because it's a term that we're going to be using for the rest of the video, is firstly, what is a gravitational field? So first things first, this isn't something that we can physically observe with the naked eye, but it's a mathematical model that explains what we observe with regard to the gravitational interactions between masses. And any body with a mass has a gravitational field. And there's four key associated concepts with a mass's gravitational field and the interactions between other bodies in that gravitational field. So the gravitational force, gravitational field strength, gravitational potential energy, and gravitational potential. So these concepts are all highly related to one another, but they differ slightly. And they all offer unique pieces of information about a gravitational field and again, those interactions. All right, so starting out with gravitational force. So gravitational force is a vector quantity, so it has both magnitude and direction. And it's defined as a force that attracts any two bodies with mass. So both of these bodies feel that force. Their direction is along the line that connects the centers of these two bodies and is dictated by Newton's law of universal gravitation. So let me just draw that out. Despite maybe what you might think would a small mass have the same effect on a larger mass, it is the exact same magnitude, just opposite directions. And the magnitude is dictated by Newton's law of universal gravitation, which states that the gravitational force felt between two bodies is proportional to the product of the masses of the two bodies. So we're going to say one of the bodies is big M, and the other body is little m, and that's with regard to their masses. Typically, the larger mass is given big M. You might also see M1 and M2. This is it's similar. It's your choice. The other part of Newton's law of universal gravitation is that this force is inversely proportional to the square of the distance between the centers of the two bodies. And the constant of proportionality that relates this side of the equation and this side of the equation is G, capital G. But it's approximately equal to 6.67 times 10 to the negative 11 Newton meters squared kilogram to the negative 2. And this is also called the universal gravitation constant. So moving on to gravitational field strength. Gravitational field strength is more general a way of describing a body's gravitational field, as it's irrespective of the mass of the other body, which is little m, that is attracted to the main body. So it's defined as the gravitational force felt by 1 kilogram point mass at some point P in a body's gravitational field. So in essence, basically what you're doing in obtaining the gravitational field strength is using the same formula as before, but setting M to 1 kilogram. Because G, the equation for G is simply Gm over R squared. So if you compare that to the previous formula, it's simply just taking F over M. So that's gravitational field strength, simple as that. All right, so let's rearrange this equation to be F equals mg. Now, this is something that you're probably very familiar with. It's the equation for weight. Now, I'm not saying that this equation is wrong. I'm just saying when you look at F equals mg, in this context, it might not always be the same thing, or in most cases, actually, it's not going to be the same thing as W equals mg. So when you think of W equals mg, you're probably thinking of G as 9.81. Where does this number come from? Actually, it's derived from the same equation that we just found for gravitational field strength. So you get 9.81 if you do Gm over R squared, where m is the mass of the Earth and r is the radius of the Earth. Because what 9.81 is the acceleration of gravity, or the gravitational field strength, at the surface of the Earth. So now when you're working with any other distance from the Earth's surface, whether that be in the Earth's, like farther in the Earth's atmosphere or closer to where the moon is. It's a different gravitational field strength at those points. So be careful in using 9.81. So if you were gonna compute gravitational force, F equals mg would only work if you had g at that point in space. All right, so in my opinion, gravitational potential energy is a little more tricky to conceptualize. It's defined as the work done in bringing two bodies to the present position from an initial distance between them of infinity. All right, that sounds like a whole lot of nothing. Let's unpack that. So for practical purposes, we consider big M to be fixed and little m to be what is taken from a distance of infinity to a point P in M's gravitational field. So gravitational potential energy is a scalar and it's measured in units of joules. So we can actually derive the formula for gravitational potential energy from this definition. So we know that the formula for work across a distance when the force isn't constant, the force that is doing the work isn't constant, this formula is equal to the integral from A to B, where A is the initial distance, B is the final distance. The integrand is F as a function of the position times ds. So in our terms, at least in the context that we're doing, the work in bringing the point mass m from a distance of infinity to some position p, which is a distance r away from big M. Our initial distance is going to be infinity, and our final position is going to be r. And as a function of r, we already know our force. We got it previously. It's gmm over r squared. And we can replace the ds with a dr. So we can solve this improper integral simply by first taking out gmm, since those are all constants with respect to r. And we can take the limit of some variable b and replace that infinity in the integrand. And then we can go about solving this integral. So what we get is, I believe, -1 over r minus or plus 1 over b, since it's a double negative. And that is when b is taken to infinity. So 1 over b, as b approaches infinity, is simply 0. So we can remove that. So then we have gmm times -1 over r. So that gives us our formula for gravitational potential energy of -gmm over r. So you normally, in perhaps units in energy or units in mechanics and things like that, when I say that, I mean class units, you normally hear the term gravitational potential energy associated with the equation UG equals mgh. Now, again, like before with W equals mg, this isn't exactly incorrect. Be careful when you're using this equation. In fact, I'd say never use this equation when it comes to gravitational potential energy at the scale that we're talking about, when it comes to planets and very, very large distances. But we can still derive this formula mgh from our equation -gmm over r. So I think the term gravitational potential energy in the context of U equals mgh can be a little deceiving because in this instance, mgh is really just the potential energy difference between the surface of the Earth and a body at a relatively small height h above the Earth's surface. So if you put that into our formula, delta U, which is the potential difference, or potential energy difference, is equal to, it looks something like that. So we have our gravitational potential energy, so the higher gravitational potential energy at our height h above the Earth's surface, and then we have the potential energy at the Earth's surface. So we can factor this into -gmm times 1 over r. I have to factor out the negative, actually. So we can factor it as such, and then we can combine those fractions to make r plus h minus r over r times r plus h. And you can see in the numerator, the r's cancel out. So we're left with gmm times h over r times r plus h. Now, this formula mgh is only really correct to use when you're close to the Earth's surface. So when you're close to the Earth's surface, r plus h can be approximated to just r. H is extremely insignificant in relation to the radius of Earth, which is normally the situation that you're going to be using mgh. So then our formula becomes gmm times h over r squared, because r plus h just becomes r. Now this can actually be rewritten, since we knew from earlier that gm over r squared is just equal to g. So if we replace gm over r squared with little g, we get mgh, which is the formula that you would use for the gravitational potential energy at the surface of the Earth. But again, just be careful with that formula mgh. Lastly, gravitational potential. Let me explain gravitational potential by saying gravitational potential is to gravitational potential energy what gravitational field strength is to gravitational force. So what I mean by that is, to get gravitational potential, you simply divide gravitational potential energy by little m. So the formula for UG, which was gravitational potential energy, was negative gmm over r. Vg, which is gravitational potential, is simply UG divided by m, which gives you negative gm over r. And so that brings us to the definition of gravitational potential. The gravitational potential at point P in a gravitational field, so let's say big M's gravitational field, is defined as the work done in bringing a 1 kilogram point mass from infinity to point P. So again, the choice of 1 kilogram is the same as the reasons that we chose 1 kilogram for the definition of gravitational field strength, because it's the same thing as if you were to just remove m from the denominator of UG's equation. All right, and that takes us to the end of the video. Thank you guys for watching. This is my first video, so it'd be awesome if you subscribed and left a like. If you have any feedback or want to say anything in the comments, feel free to, and I'll be sure to respond. And stay tuned for the next video on the actual code behind this gravitational quantities visualizer. Cheers.